In this video, we are continuing our discussion of numerical differentiation. And in particular, we're talking about high accuracy numerical differentiation formulas. So the formulas presented in the previous sections for the forward and backward finite difference have an error term of order h, while those for the centered finite difference scheme have an error term of order h squared. It is possible to provide formulas with less error by utilizing more terms in the Taylor approximation. In essence, by increasing the number of terms in the Taylor series approximation, we assume a higher order polynomial for the approximation, which increases the accuracy of the derivatives. In the following presentation, the function f is assumed to be smooth and the points are equidistant with a step size of h. First, let's start with the forward finite difference technique. According to the Taylor theorem, the function at xi plus 1 is equal to f at xi plus f prime at xi times h plus f double prime xi over 2 factorial h squared plus an error term of order h cubed. Now, if we plug in the forward finite difference equation for f double prime at xi here, then we can write this out all in terms of the function values, and then we can rearrange for f prime at xi. So you can see the expression here, and then we can divide through by h to get that the derivative at xi, so f prime at xi, can be approximated by minus f xi plus 2 plus 4 f of xi plus 1 minus 3 f of xi all divided by 2h, with this approximation having an order h squared. So this equation provides an error term that is directly proportional to the square of the step size, indicating higher accuracy than the basic formula of section 10.2. Using the same procedure, the following equations can be obtained for the second, third, and fourth derivatives. So you can see that the second derivative depends on the function value at xi, as well as the 3 points after that, xi plus 1, xi plus 2, and xi plus 3. The third derivative depends on the function value at xi, as well as the 4 points after that, up to xi plus 4. And the fourth derivative depends on the function value at xi, as well as the 5 points after it, up to xi plus 5. And all of these are order h squared for the forward finite difference technique. We can follow the same procedure for the backward finite difference. So again, according to the Taylor theorem, we have that f of xi minus 1 is equal to f of xi minus f prime xi times h plus f double prime xi over 2 factorial h squared plus an error term of order h cubed. We can use the backward finite difference equation for f double prime of xi to get this all in terms of the function values when we rearrange for f prime of x at xi. Here we can then divide through by h, and we find that the expression for f prime of xi is equal to this function that has depends on the function value at xi, as well as the 2 points preceding it, xi minus 1 and xi minus 2, and here it is order h squared. So again, this equation provides an error term that is directly proportional to the square of the step size, indicating higher accuracy than the basic formula of section 10.2. Using the same procedure, the following equations can be obtained for the second, third, and fourth derivatives. So the second derivative depends on the value of the function at xi, as well as the 3 points before it, and it is order h squared. The third derivative depends on the value of the function at xi, as well as the 4 points before it, up to xi minus 4. And the fourth derivative depends on the function value at xi, as well as the 5 points before it, up to xi minus 5. And all of these are order h squared for the backward finite difference technique. Now we can talk about the centered finite difference technique. So according to the Taylor theorem, we can represent the function value at xi plus 1 as shown here, with an error term here up to order of h to the power of 5. We can do the same thing for the function value at xi minus 1, with again up to the order of h to the power of 5 for the error. Then we subtract these two equations and use the centered finite difference equation for the third derivative. So when we subtract these two equations, these terms will cancel out, these terms will cancel out, and then we can plug in the centered finite difference equation for the third derivative terms, and that goes here. And then we rearrange for the first derivative term, which we have here. So now this depends only on the function values at our various points. We can divide through by 2h, and we get that the first derivative at xi can be approximated with the expression shown here, which is dependent on the function values at xi plus 1 and xi plus 2, as well as xi minus 1 and xi minus 2, and it is order h to the power 4. Using the same procedure, the following equations can be obtained for the second, third, and fourth derivatives. So this is the expression for the second derivative, which depends on the function values at the point we're interested in, xi, as well as 2 points before it, xi minus 1 and xi minus 2, and 2 points after it, xi plus 1 and xi plus 2. The third derivative depends on the function values 3 points before the one we're interested in, so xi minus 1 to xi minus 3, and 3 points after, so xi plus 1 to xi plus 3. And the fourth derivative depends on the function value at the point we're interested in, as well as 3 points before it and 3 points after it. And all of these are order h to the power 4. So again, these provide a better approximation for these higher order derivatives compared to the forward and backward finite difference schemes. Here the error is order h4, and in the previous schemes, the forward and backward finite differences, the error was order h squared. And all of these formulas that we've introduced here provide higher accuracy than the basic formulas that we discussed in section 10.2.